did you know today? This is actually an electrolysis example, and we're going to look at how similar it is to what we've been doing. We've been looking at voltaic or galvanic cells. The only difference between a voltaic cell and an electrolytic cell is electrolytic is not spontaneous. And I'll put the table up that shows both on the next slide. But everything else we still look at the same way. We still look at cell potential the same way. We still look at canceling out electrons the same way. It's just the setup of the cell is a little bit different because the reaction doesn't run on its own. So this says a sample of water is electrolyzed. So electrolyzed means it's going to be in an electrolytic cell. When it says that water is electrolyzed, that means that water is broken up. And I'm going to actually show you what the electrolysis of water looks like as a demo. I'll show you how we can actually separate water into H2 gas and O2 gas. So it shows the setup over here. You have water in a beaker, and you can electrolyze water. You can break it apart into H2 gas and O2 gas, and you can actually collect that gas. So it says a sample of water is electrolyzed under standard conditions as shown in the diagram. Part A says write the balanced equation for the water electrolysis reaction. Up here they give us two half reactions. Whenever they give you half reactions with potentials, those are reduction potentials. So they're showing us both reduction reactions. Now, just like a voltaic cell, you always need one oxidation and one reduction half reaction. Now, here's the thing with water being electrolyzed. That means that water is being broken apart. Water needs to be a reactant. So for both half reactions, water should be a reactant, and we're producing H2 and O2 gas. So if we take a look at these half reactions, I see H2O as a reactant in this second half reaction. So this half reaction is okay. I can leave this alone for now. Up here, I see that water is a product. Well, just like we were doing with voltaic cells, we always left one reaction alone, and one of them we had to flip. Because what this is showing is that this is the reduction half reaction, because it's the reduction potential, which means this one should represent the oxidation half reaction. And if we want to represent oxidation, we have to flip the reaction. So we want to flip this. I'm going to rewrite the flipped equation up here. 2H2O liquid yields O2 gas plus 4H plus, which is aqueous, plus 4 electrons. Now if you say, well, why do we need H plus? Why do we have O2 and H plus? Well, remember when we balance redox, initially it would have just been H2O yields O2. Then you balance the atoms, you balance O's with water, you balance H's with H plus. So that's how we actually get this entire balanced half reaction. So they actually did the balancing of the half reaction for us already. Now we want the overall equation for everything that's happening in this cell. Well, this is what we did with voltaic cells already. Before we can add these two together, what do we have to make sure to do so that they cancel? Make the electrons equal. So up here we have 4 electrons, down here we have 2 electrons. So there are 2 ways you could actually make them equal. One of the ways, and it was the way that I would have looked at initially, is I would actually multiply this entire second half reaction by 2. Because when I multiply the entire second half reaction by 2, this becomes 4, this becomes 4, 2, and 4. What you could have done as well is you could have multiplied the top half reaction by 1/2 to make them equal to 2 electrons. Either one works. So now I have 4 electrons on each side. I'm going to rewrite the equation down here so we can do some canceling. So we have 2H2O yields O2 gas plus 4H plus 4 electrons. And then the second half reaction, we have 4H2O plus 4 electrons yields 2H2 gas plus 4 OH minus. So taking a look at this, what can we cancel? The electrons. 4 electrons on the right, 4 electrons on the left. So if we have to ever calculate anything and we need N, we need the number of moles of electrons, that's 4. 4 electrons were transferred between the two half reactions. And then remember, you can combine. So here we have 2H2O and 4H2O. So if I add these together, I'm going to have 6H2O yields O2 gas plus 4H plus, which is aqueous, plus 2H2 gas plus 4 OH minus aqueous. There's one more thing we can actually do here. Notice on the products you have H plus and OH minus. If H plus and OH minus are added together, what does that create? H2O. So 4H plus and 4 OH minus will create 4H2O. Well, now notice we can cancel more waters. So you always want to look for things that can add together, which is H plus and OH minus, and then you can cancel out. So if I have 4 H2Os on the right now and I have 6 over on the left, I can actually cancel 4 of them out and get 2 H2O liquid yields O2 gas plus 2 H2 gas. So we canceled out the electrons. And then when we canceled out the electrons and added things together, we were able to actually create more water and cancel out more water molecules. So here's our balanced equation for the electrolysis of water. This is what is happening in this entire cell. Each of the half reactions is showing each one of the electrodes, but then this is showing everything. So then part B says calculate the standard cell potential. So cell potential is just like what we've been looking at before. E naught of the cell is the reduction half reaction plus the oxidation half reaction. So if we take a look at everything up here, 2H2O yields O2 plus 4H plus. So we had to flip this one. This was oxidation. If we flipped the reaction, what do we have to do to E? Make it negative. Remember, it does not matter if you have to multiply the reactions to get the electrons to cancel. The only thing you do to E is change the sign. That's the only thing you can do to potential is change the sign. And then this one we leave alone because we didn't do anything to the reaction itself. Yes, we multiplied by 2, but that doesn't matter. Voltage is a ratio. So since we didn't flip the reaction, we leave E alone. So that means that cell potential will be negative 0.83 volts plus negative 0.70 volts. The reduction half reaction was negative 0.83. The oxidation was negative 0.7. Right up here in box it. E naught cell is negative 1.53 volts. If you look at this and say, well, it's negative. Yes, because it's an electrolytic cell. Electrolytic cells have negative cell potentials. It is not a spontaneous reaction on its own. That's why if you notice in the diagram here, there's a battery. The battery is what pushes the electrons through the wire. Pushes the electrons or pulls the electrons, depending on the side of the battery. Electrolytic cells need a power source. And then part C, determine the standard free energy of reaction for this reaction. Free energy is delta G. Remember, you have the equations on your equation sheet. This E cell you don't have on your equation sheet, but delta G you do. To calculate delta G, if you have voltage, it's negative N times F times E naught. N is the number of moles of electrons that were transferred. That is the number of electrons that you crossed out in the half reactions. So the number of electrons that we crossed out in the half reactions was 4. We made them both equal to 4. So negative 4. F is Faraday's constant. That is also on your equation sheet. You do not have to memorize Faraday's constant. It's 96,485. So it's 96,485 coulombs per mole of electron. And then E naught is the voltage, negative 1.53. Don't forget your negatives. Volts is a joule per coulomb. So when you solve for delta G, it comes out in joules. Ooh, big number. Remember, this is in joules. 590,488 joules. Which is why it always is nice to put it in kilojoules, because the number is easier to work with. So once you get your answer, you divide it by 1,000, you get 590.5 kilojoules. You just have 590 to 3 sig figs, that's okay. Notice with both of these, E naught cell is negative, delta G is positive. When you have a negative E cell and a positive delta G, what does that tell us about this reaction overall? It's non-spontaneous, right? Or it's not thermodynamically favored, which is why an electrolytic cell needs a battery to work. So notice it was done the same way. Everything was done the same. You still need an anode, you still need a cathode. The difference is that when we see electrolysis, it's almost always water that we're dealing with, at least on AP questions. So when it says water is electrolyzed, that means we're dealing with an electrolytic cell. We're breaking water apart. Breaking it apart into its elements, in this case H2 gas and O2 gas. Questions on the do now? So just really quick, I want to compare the two types of cells. So this is actually right out of your notes. Do nows will get turned in. I put the assignment on Classroom, so you'll have some time during the next period that you can always just upload your do now. So for this, comparing the two cells, this information right in the middle of the slide is right out of your notes. Right, these two are right out of your notes. It's on page 14, right up here at the top. You don't have to worry about writing these down. The difference between the two types of cells, galvanic, remember that's Voltaic. Those are the cells we've been working with so far. It's a thermodynamically favored reaction, so it's spontaneous. We have the anode on one side, the cathode on the other. They're separated by a salt bridge, and it produces electrical energy. It's a positive voltage because it happens on its own. Electrolytic looks like this, and you have this picture in your notes on the page before. It is an unfavorable reaction. It's not spontaneous. You have the anode and the cathode in the same container. I'm going to show you what it looks like with water. Or you can have a solution of a salt. So remember, aqueous, AQ, means that the substance is dissolved in water. Molten is liquid form. So if it's molten NaCl, it's liquid NaCl. Aqueous NaCl means NaCl is dissolved in water. You don't need a salt bridge because everything is in the same solution, but you do need a power source. You have to have a power source to make the reaction work because it's not spontaneous. And so it uses electrical energy. It's a negative voltage. So I like this table because it compares both. And in both types of cells, you still have oxidation at the anode, reduction at the cathode. That doesn't change. You still have anions flowing toward the anode and cations flowing toward the cathode. Electrons are still flowing from the anode to the cathode. That doesn't change. The only difference is that electrolytic cells do not happen on their own. And so since they don't happen on their own, we need a battery to make them happen. So I'm going to go through just a quick demo before you have some time to work on mastering. Before we go through this, just a quick thing on overvoltage. So I talked about overvoltage in the video on electrolysis and electrolytic cells. Overvoltage is not tested anymore. So the idea that instead of Na plus or Cl minus undergoing oxidation or reduction, you could have water in its place. We won't test on overvoltage, but overvoltage is good to know about because when we see an electrolytic cell, we don't always get the products that we expect, and that's due to overvoltage. So I talked about it in the video, but you will not be quizzed or tested over the idea of overvoltage. So what I'm going to show you guys really quick is the electrolysis of water. So in this Petri dish, there's some water, and then I have a 9-volt battery, right? So 9 volts means it can put out 9 volts of potential. And then I have these what are called alligator clips, and they're connected to pencil lead. So the pencil lead is actually going to act as our electrodes because pencil lead is made of carbon. So carbon is an inert electrode, meaning that the pencil lead is just a way for the electrons to flow into the solution. So what I'm going to do is I'm going to take the other side. So these alligator clips actually have 2 sides, right? There's a wire that connects them. And I'm going to take the side that is not connected to the pencil lead, and I'm going to connect it to the battery. So I'm going to put one side on one terminal of the battery. I'm going to put the other side on the other terminal. So we have them connected to opposite terminals. And then I'm going to put the electrodes into the solution. So it's hard to see here. I'm going to see if I put it on the black surface, if that makes a difference. Don't mind the masking tape from showing everything before. So let's see if we can see what happens here. So now, can you guys see what's happening on the pencil lead? Yeah, so notice on this black electrode, right, the black clip, you have lots and lots of bubbles coming off. The other side, you have some bubbles, but not as much. So let's see if I can zoom in just a little bit more. See if we can get it even closer. So now you can see. So both sides are bubbling. One side is bubbling more than another. If I remove one electrode, the bubbling stops on this side. You have to have both electrodes into the solution for electrolysis to work. So again, this is water in this Petri dish. One side is producing much more gas than the other. Well, if we think about it, water is H2O. There's twice as much hydrogen as oxygen. So we have twice as much. Hello? Yes. Nope. Yep. So water is H2O. So there's twice as much hydrogen as oxygen. So when we see this, we're actually producing twice as much hydrogen gas on this black clip electrode than on the red. So the black one is H2, the red one is O2. And so what I was doing as I was putting those electrons into the water is I was breaking water up into H2 gas and O2 gas. That was undergoing electrolysis. But the difference is, right, they're in the same, the water's in the same container. So we don't need two separate containers like we did. Well, I'll just show you this, right, like we did with this Voltaic cell. So this was a Voltaic cell where you had the anode on one side, the cathode on the other. You had the voltmeter, the salt bridge. With electrolytic, it's all taking place in just one container. So that's looking at electrolytic cells, looking at the electrolysis of water. I'm going to give you guys time now to work on mastering. So you can grab a marker if you don't have one already. You can get with a partner. You can move around. Work on mastering. Remember, they're broken apart by video. So you have, I think, 2 questions with free energy, just 2 questions with electrolysis. But the electrolysis questions we won't get to until Monday. So there's actually math questions that go along with electrolysis that we'll look at on Monday that deals with electroplating. So how you can actually put like a film or a layer of gold or a layer of silver on top of something.